Hello, everyone. Welcome to section 4.5. This section will be talking about solving exponential and logarithmic equations. So let's go ahead and start off with simpler equations. So here are some rules about logarithmic and exponential equations that are particularly useful for simpler ones. There's two of them. The first one for exponential equations is that if you have some number a, 2 or 3 or 14 or whatever, you raise it to the x power, and you say that that's going to be equal to that same base raised to the y power, then this means that we can say x equals y. Okay? And similarly for logs, if you have a log base some number a of x equal to log base the same number a of y, then that means that we can say x equals y. These facts come from the fact that exponentiation, so a to the x, and logarithms, so log base a of x, are both one-to-one functions. Okay, so these two little rules are very useful if we're trying to solve simpler ones, as I said. Let's go ahead and take a look at an example as to how we can use them. So let's say, for example, we wanted to solve something like 3 to the 2x plus 1 equals 27. Okay. Now, 27 is 9 times 3, and 9 is 3 times 3, so 27 is 3 cubed. So we can rewrite this equation as this. Now, I have 3 raised to a power, and I have 3 raised to a power on both sides. So the base has to be the same. In this case, they're both 3. So what we can go ahead and say is 2x plus 1 equals 3, where the 2x plus 1 came from here, and that 3 right here came from this power. And now this is just a linear equation. We know how to solve it. Subtract 1 from both sides and divide both sides by 2. Look at that. Pretty straightforward. Let's see an example with logarithms. Let's say we wanted to solve something like log base 5 of x plus log base 5 of x plus 1. Let's say we want that to be equal to log base 5 of 6. Okay. To start off, I'm going to go ahead and use one of the logarithm rules to combine the two logs on the left-hand side. So I'm going to write this as log base 5 of x times x plus 1. And that's equal to log base 5 of 6 from the other side. Okay, so now notice that we have a log base 5 and a log base 5 on both sides. And since they're the same base, they have to be the same base for this move to work. Since they're the same base, we can go ahead and say that x times x plus 1 equals 6. And now we can go ahead and solve for x like we've been doing in the past chapters. I'm going to go ahead and FOIL out that left-hand side. So we get x squared plus x equals 6. And then I'm going to subtract both sides by 6. We get an x squared plus x minus 6 equals 0. And then you can go ahead and factor this. I think you get x plus 3 times x minus 2 equals 0. And this tells us that x has to be negative 3 and 2. All right, so pretty straightforward for solving simpler ones like this. But sometimes these equations get trickier. So in tackling those, let's go ahead and talk about exponential functions, or not exponential functions, exponential equations first. So steps for harder exponential equations. So the steps for these, if you have an exponential, let me try again. If you have a exponential equation, and just using those simple rules that we looked at the beginning of the video aren't really helping, these are the steps that you should try and follow. So the first step is going to be to isolate the exponential expression on one side of the equation. Okay. Once you've done that, the second step is you're going to take the log of both sides of your equation to sort of undo the exponent. And this is using property number 3 of logarithms. And then the last step is going to just be solve for the variable. Let's see these steps in actions. Maybe they'll make a little more sense once we see them in a concrete setting. So let's say, for example, I wanted to solve something like 8 to the x equals 125. So you can go ahead and try to use the simpler rules that we looked at earlier, but I don't think they'll work out very nicely for you, just because 125 works out to be a power of 5, actually, and not a power of 8. So that kind of approach won't really work. But we can go ahead and use the steps we just talked about. So the first step was isolate the exponential expression on one side of the equation. It's actually already done for us. We have the a to the x on one side, and then everything else, in this case, just 125 on the other. So now we can just go ahead and do step 2. We want to take the log of both sides to undo the exponentiation. We want to take a log base 8. That way we get rid of the 8 to the x. So we do log base 8 of 8 to the x equals log base 8 of 125. And then we can go ahead and use some log properties, property number 3. And we can rewrite the thing on the left-hand side as just x. Log base 8 of 8 to the x is just going to be x. And that's going to be equal to log base 8 of 125. Okay, cool. At this point, you have solved for the variable, but we could make this a little bit nicer if we wanted to. But this is perfectly fine as an answer. I'll show you a way you could clean this up. You could go ahead and use the change of base formula. You could write this as log base 2 of 125 over log base 2 of 8. And the reason I did that is because 8 is a power of 2. In fact, log base 2 of 8 is going to be 3. So you get this. And then I'm going to rewrite this a little bit clearer. This is 1/3 times log base 2 of 125. And then we could use one of the log laws to move that 1/3 up as an exponent of 125. So we get x equals log base 2 of 125 to the 1/3. The cube root of 125 is 5. 5 times 5 times 5 is 125. So this is x equals log base 2 of 5, which is a cleaner answer, a little bit nicer. Okay, cool. So let's go ahead and look at maybe another example, something we might see. Let's say we wanted to solve for x, and we had 9 to the x over 2 power equals 5 times 1 minus x. This one's a little bit funkier. But let's go ahead and do the first step, which is we want to isolate the exponential expression on one side of the equation. So I'm going to go ahead and divide both sides by 5 to the 1 minus x power. And so we get 9 to the x over 2 power over 5 to the 1 minus x power. And that's going to be equal to 1. And then I'm going to use some exponent rules that we saw in chapter 1. I'm going to write the 9 to the x over half power as 9 to the 1/2 to the x, like that. And then I'm going to write this 5 to the 1 minus x as 5 to the 1 times 5 to the negative x. And that all equals 1. Okay. I'm going to go ahead and multiply both sides by 5. So that now we have 9 to the 1/2 to the x over 5 to the negative x power equals 5. So I just multiplied both sides by 5, and those canceled. So that's what I did right there. And then I'm going to go ahead and flip the 5 to the negative x power over to the numerator, and I'm going to rewrite that 9 to the 1/2 as 3, because the square root of 9 is 3. So we get 3 to the x times 5 to the negative x is just going to be x, and that's equal to 5. And now we can go ahead and pull the exponent off because it's multiplication. So we get 3 times 5 to the x. That equals 5. So now we have 15x equals 5. Okay, so we've isolated the exponential expression. Took a little bit of work, but we got there. Now we're going to go ahead and apply log base 15 to both sides. So we'll do log base 15 of 15 to the x equals log base 15 of 5. And then this just becomes x equals log base 15 of 5. I don't think there's a simpler way to write this. I think this is the cleanest way we can do it. Okay, cool. So it takes a little bit of work, but if you follow the steps, it should help you stay on track to solve these problems. Let's go ahead and look at one more example. Let's go ahead and do 125x plus 5 to the 3x minus 1 equals 200. Okay, 125, I think, as I mentioned previously, is going to be 5 cubed. So I'm going to go ahead and write that. So we have 5 cubed to the x plus, 5 to the 3x minus 1 equals 200. And then I'm going to go ahead and use exponent rules to write this as 5 to the 3x plus 5 to the 3x minus 1 equals 200. And now exponents don't really play nice with addition, so we have to do a little bit more work. I'm going to go ahead and pull a factor of 5 to the 3x out from both terms. And the way I'm going to do that is I'm going to first write this second term as 5 to the 3x times 5 to the negative 1 equals 200. And then I can pull that 5 to the 3x factor out of both terms, and I get 5 to the 3x times 1 plus 5 to the negative 1 equals 200. We can simplify that expression in the parentheses a little bit as 1 plus 1/5, so 6/5 equals 200. And then I can divide both sides by 6/5 to get 5 to the 3x equals 200 times 5/6, which, if you do some math, simplifies. I guess it's simpler to write 500 over 3. Okay, now we've isolated the expression. We can take the log base 5 of both sides. So we'll do log base 5 of 5 to the 3x power equals log base 5 of 500 over 3. And then using our property number 3, we have that 3x equals log base 5 of 500 over 3. And then we can go ahead and just divide both sides by 3. And we just get x equals 1/3 times log base 5 of 500 over 3. And I actually think this might be the simplest way to write it. Okay, cool. So that was exponential equations. Now, let's go ahead and shift gears and let's talk about logarithmic equations. It turns out that the steps are very, very similar. So we should be able to apply a lot of the sort of knowledge and skills that we've kind of built up with exponential equations to logarithmic equations. So let's just go ahead and write out the steps for logarithmic equations, just like we did for exponential equations. That way we have everything all on one page. So always steps for harder logarithmic equations. Okay. As with the first step in exponential equations, the first step here is we're going to isolate the logarithmic expression on one side. On one side of the equation. And just like with exponential equations, the second step, or rather a little bit flipped from exponential equations. So instead of taking the log of both sides, once you have the logarithmic expression isolated, you're going to want to exponentiate both sides. Of that equation. And that's to undo the log. Same kind of move, just a little bit flipped. That's using property number 4 of logarithms. And then step 3 is solve for the variable. Okay, let's look at some examples. So maybe we want to solve something that looks like ln of x equals 15. Remember, ln is the natural log, that's log base e. So we already have the logarithmic expression isolated on one side. Let's go ahead and exponentiate. Because ln is log base e, we want to raise both sides to the e, or rather, we want to take both sides of this equation and have them as the exponents to e, right? So we got e to the ln of x power equals e to the 15. And then, let me clean that up a little bit. Because ln is log base e and it's raised, and we've got e raised to the natural log of something, we just get that x equals e to the 15. That's using property number 4 of logs. Okay, let's maybe look at a different equation. Let's do common logs this time. Let's say we have log base 10, so just a common log of x plus log of x minus 1 equals log of 4x. Now, you could actually solve this one using the simpler method, but I'm going to go ahead and show you with the steps that are for the more complicated equations, just so we can get used to using those. So first, I'm going to go ahead and combine the two logs on the left-hand side using one of the log laws. So we get log of x times x minus 1 equals log of 4x. And then because the common log is log base 10, we're going to raise both sides as a power of 10. So we get 10 to the log of x minus 1 equals 10 to the log of 4x. And now we can use property number 4 of logs on both sides of the equation. And we get that x times x minus 1 is equal to 4x. And now we can go ahead and solve for x like we usually would. We can FOIL out that left-hand side. We get x squared minus x equals 4x. We can move that 4x to the other side. So we get x squared minus 5x equals 0. And then I can just pull out a factor of x from both terms. So we get x times x minus 5 equals 0. And so we know that x has to be equal to 0 or 5. All right, let's look at one more example, maybe something a little funkier. Let's say we had log base 2 of log base 3 of x. And let's say that's equal to 4. A little funky. Okay, but let's keep our wits about us. Let's go ahead and follow some steps. So the logarithm expressions there, they're all on one side. There's no logs on the other, and there's only logs on the left-hand side. So the first log on the outside is base 2. So I'm going to go ahead and have both sides of this equation as exponents of 2. So I'm going to raise 2 to the log base 2 of log base 3 of x equals 2 to the 4. And so now we can go ahead and use that property. And you can think of it as this 2 and the log 2 cancel out in some ways. And so you get log base 3 of x equals 2 to the 4th, which is 16. Okay, now we can do the same thing again, but this time with 3. So we will have 3 to the log base 3 of x equals 3 to the 16th. And those cancel out again, and we get x equals 3 to the 16th. And this would be a perfectly acceptable answer because 3 to the 16 is a massive number. It's something like 43,046. I guess that's 43,046,721. It's a pretty big number. So this is a good answer. Okay. Before we wrap up for today, let's discuss briefly applications. Just real quick. Let's say we had a word problem. Jeffrey invests $5,000 in an account that pays 8.5% interest. And let's say it's, so this is interest a year, and that's compounded continuously. We want to know how long will it take, not how long will it take to double their investment? So this is a continuously compounded interest problem. So recall the formula for this was A of t equals PERT, where P is the principal and T is time and R is the interest rate. And so the principal is how much they invested in the beginning. So it's going to be $5,000 times E to the rate, which is 8.5%. So it's going to be 0.085 times T. Okay, and we want to know when it doubles. So which will be 5,000 times 2, which is 10,000. So what we're going to do is, so remember the A of t is how much money you have after t time. So we want to set A of t equal to 10,000. And then we have 10,000 equals 5,000 times e to the 0.085 t. And we want to solve for t. We want to know how much time this is going to take. Okay, so let's go ahead and divide both sides by 5,000. So we get 2 equals e 0.085 times t. And now we can go ahead and take the natural log of both sides. So we'll do natural log of 2 equals natural log of e to the 0.085 times t. And then these two things cancel out. So we get natural log of 2 equals 0.085 times t. And we can divide both sides by 0.085 and we get t is equal to 0.085 over, flip those around. Oopsies. T is going to be the natural log of 2 on top divided by 0.085. There we go. And this is a perfectly acceptable answer because we're not using calculators in this course. But just for your information, this is about 8.2 years. But this is good. All right, so that's solving logarithmic and exponential equations. This stuff's pretty bread and butter, just like solving other kinds of equations. So let me know if you have any trouble with it at all. I'm happy to chat about it.